Hi there, folks. This is the Practice Chapter 5 test, and as always, I am the amazing Mr. Jansen. So away we go. If we look at these first two, we're finding a couple different things here, starting with increasing and decreasing. Remember, increasing is when the function essentially has a positive slope, and decreasing when it has a negative slope. And we're always looking at increasing and decreasing, going from left to right on the function. So on this one, it looks like it starts off decreasing, so it's going down, and then it switches to increasing, it's going up. And then it's decreasing again, it's going down, and then increasing. And then basically what I want to do here is I'm going to label this in interval notation, and I just essentially label the x values. So from here to here, the x values go from negative infinity to negative 3, and it's decreasing on that interval. So from negative infinity, let me write that down here, decreasing. From negative infinity to negative 3, it's decreasing, it's going down. And then the function from here to here, from this value, from the negative 3 until I get to here to the 0, it's going up, it's increasing. Negative 3 to 0, it's increasing. And then from 0 to positive 3, from here to here, it's going down, it's decreasing. So that goes in my decreasing section. And then from here on up, it's increasing, and that's all the way to positive infinity. So I say 3 to infinity. So again, I'm just going left to right on my function. What's the function doing? From here to here, it's going up. From here to here, it's going down, increasing and decreasing. Relative maximums and minimums. The reason I use parentheses on each of these things is because the values in between here, it's neither increasing or decreasing because those are turning points. And actually, these two turning points are my relative minimums. This one up here is my relative maximum. Okay, so I've got a relative maximum at 0, 0. Again, it's just a high point when the function goes from increasing to decreasing. Relative minimums, I've got one at negative 3, negative 4. And then I have another one at 3, negative 6. And again, they're relative. They're minimums relative to the points around them. It's when the function goes from decreasing to increasing. And then end behavior. End behavior I always describe in terms of what x is doing and then what y is doing. So I look at it as x is going to negative infinity and then as x is going to positive infinity. And really, that's how we define end behavior, is what the function does as x goes to plus or minus infinity. So now when I look at this, as x goes to negative infinity, essentially I'm looking at the left side of my graph. So I'm looking at this piece right here. And I just look at the arrow on that end. The arrow is going up, so my f of x is going to positive infinity. And then as x goes to positive infinity, which is the right side of my graph, I look at my arrow, it's going up. So f of x is going to positive infinity. So that's my end behavior. As x goes to negative infinity, f of x goes to positive infinity. As x goes to positive infinity, f of x goes to negative infinity. Okay? Taking a look at the next one. Again, I just go left to right. Here I'm going up, it's increasing. And then I'm going down, it's decreasing. And then it's going back up again, it's increasing. And just like before, I have these turning points where it's neither increasing or decreasing, which essentially means I'm going to be using parentheses when I talk about interval notation. But now I do the same thing. In this one, from here, from this edge until I get to this value right here, the function is going up. It's increasing. That was from negative infinity to negative 2. So from negative infinity to negative 2, it's increasing. Those values are not included, so I use parentheses. And then from negative 2 until I get to this value right here, from negative 2 to positive 1, it's decreasing. It's going down. So from negative 2 to positive 1. And then from positive 1 on up, it's increasing again, so from 1 to infinity, it's increasing. Okay, increasing and decreasing. And then relative maximums. I've got a relative maximum right here at the ordered pair negative 2, 3. And I've got a relative minimum right here at the ordered pair 1, negative 3. Again, they're maximums or minimum relative to the points around them. And then end behavior. End behavior always starts off the same way. I look at it as x goes to negative infinity, and then I look as x goes to positive infinity, and then I see what f of x does. If I'm looking at negative infinity, as x goes to negative infinity, that's the left side of my graph. I look at my arrow, it's going down, so f of x is going to negative infinity. As x goes to positive infinity, I'm looking at the right side of my graph. I look at the arrow, it's going up, so that means f of x is going to positive infinity. Okay, and that's my end behavior. Looking at end behavior algebraically, I still start off the same way I did in the previous problem. I look as x goes to negative infinity, and I look as x goes to positive infinity. But this time I'm just going to plug it in algebraically and see what f of x does. When it's in standard form like this, I essentially ignore everything except for the term with the highest exponent here. And the reason for that is because it's increasing so much more rapidly than the rest of this thing that everything else essentially becomes unimportant. Okay? So I plug the negative infinity in, and we're just going to plug this in. So I plug a negative infinity in here. Negative infinity to the 6th power is a positive infinity, times a negative 2 is a negative infinity. So as I plug a negative infinity in, as x goes to negative infinity, f of x also goes to negative infinity. And now I plug a positive infinity in, so I plug it in for x. Positive infinity to the 6th power is a positive infinity, times a negative 2 is a negative infinity. So f of x is still going to negative infinity. And that's it. That's my end behavior. If I look at the next one, I'm going to start off the same way. So I'm looking as x goes to negative infinity, and I look as x goes to positive infinity. And then I'm just going to plug each of these in to see what f of x does. And these are not in standard form, so I have to plug it in for all of the x values. So when I plug the negative infinity in, it's going to look like this, a negative infinity squared. When I plug it into each of these, infinity plus 3 is still infinity, so I kind of ignore those things that are going on around it. I'm really concerned with the signs. When I plug the infinity, sorry, that should be a negative infinity I'm plugging in first. When I do a negative infinity times 2 minus 1 is still a negative infinity. And now I start just doing the operations here. Negative infinity squared is a positive, and then I tack on this negative sign that's out front. This is still just a negative infinity here. Negative infinity squared is a positive infinity. So now I have a negative times a positive, which is a positive infinity. Okay? And then I got to do the same thing with the positive infinity. So as I plugged in the negative infinity, this went to positive infinity. And now I plug in a positive infinity. So I've got negative infinity squared times infinity to the 2nd power. And now I just start doing the operations here. Infinity squared is a positive times the negative is a negative infinity out front here. That's just an infinity. And then infinity squared is still positive infinity. So now negative times a positive is a negative. So as x goes to positive infinity, f of x goes to negative infinity. Okay, that's end behavior. If I look at the next one, I want to draw a possible sketch. So the first thing I do is I find my x-intercepts. So my x-intercepts, I just set each factor equal to 0. And I solve each. This first one, I would essentially multiply each side by a negative 2, which is going to tell me that x equals 0. Here I would add the 4, which gives me x equals 4. And here I would subtract the 3, which gives me x equals a negative 3. And these are my x-intercepts. I've got the negative 3 back here somewhere. I've got the 0 up here somewhere. And I've got the 4 up here somewhere. So I plot each of those x-intercepts. And now really I just need to determine what's happening with this thing. The first thing I think about is multiplicity. The multiplicity is how many times each solution occurs. This one, that solution occurred once. So they all occur once. When the multiplicity is odd, we pass through that point on the x-axis, which means my graph either looks like this as I pass through each of those points, or my graph is going to look like this as I pass through each of those points. And the thing that determines it is really the end behavior. Each of these is facing a different direction, so I'm going to find the end behavior to determine what this thing is supposed to look like. So as x goes to negative infinity, I plug the negative infinity in. Negative infinity times a negative, that gives me a positive right here, times a negative, which looks like a positive infinity. And then when I plug the positive infinity in, I've got a positive infinity times a negative out front, which is a negative, times a positive, which is a negative infinity. So now that I have my end behavior, I look at each end. As x goes to negative infinity, the left side of my graph, the function should be going up. The right side of my graph, the function should be going down. I wrote a positive infinity here, and so it's a negative. The right side of my function, it should be going down, which means I have to approach this point. I have to go through this point, and then through the last point, and head down forever. Okay? So my end behavior kind of narrows down what this graph has to look like. And really the useful part of this is it narrows down the fact that there is a local or a relative minimum between -3 and 0 and a relative maximum between 0 and 4. Okay, but that's my quick sketch. If I look at the next one, I do the same thing. So I've got a factor of x here. So I do x equals 0, I do the x plus 5 equals 0, and I do the x minus 2 equals 0. And then I find out that x equals 0, x equals a -5, and x equals a positive 2. So these are my x-intercepts. And now I want to talk about multiplicity. Multiplicity is how many times each of these occurs. And when you look at this, since this was an x squared, essentially that means I would do the x equals 0 twice. Because that's what x squared is. It's an x times an x. So I do x equals 0 and then x equals 0 again, which means I got this solution twice. All right, so the multiplicity of that solution is 2. The x plus 5, there's only one of those, so the multiplicity is 1. This one right here, the x squared, the fact that this thing is squared means I would have the x minus 2 written down twice, which means I would get this solution twice, essentially, which means it has a multiplicity of 2. And what this tells me is that when we have a multiplicity that's even, is I'm just going to touch at that value, which means my graph essentially has two options here. I'm going to pass through this point, and then I'm just going to touch at each of these points. Okay, almost like a vertex that's just touching. Or my function go the other way. I have to go through this point and just touch at each of these points. So my function could look like this. So again, it comes down to the end behavior here. I have to determine the end behavior to figure out which of these graphs essentially I'm going to have. So as x goes to -infinity, I'm going to plug that in, see what f of x does. When I plug the -infinity in, -infinity squared is a positive, times a -infinity, and -infinity squared is a positive. So I've got a positive times a positive, which is a -infinity. And then I plug the positive infinity in, so as x goes to positive infinity, I want to see what f of x is going to do. Positive infinity squared is a positive, times a positive, and then a positive infinity squared is, again, a positive. So when I plug this in, I get a positive infinity. And so now my end behavior tells me that the left side of the graph should be going down, the right side of the graph should be going up, and I know I have to pass through this point, touch at this point, touch at this point, and then head off to infinity. Okay, so my graph has to look something like this. And once again, it shows me that there's got to be a relative max between -5 and 0, and between 0 and 2. It also tells me that my x-intercept at 0 is a relative minimum. My x-intercept at 2 is also a relative minimum. But that's my quick sketch of the graph.